ChemExam Explained, where the aim is chemistry clarity, exam mastery. In today's video, we will be looking at CAPE Chemistry 2019, Module 2, Kinetics and Equilibria. Let's go. 2A Part 1. Using the Bronsted-Lowry theory, differentiate between a strong acid and a weak acid. A strong acid dissociates completely into its aqueous ions. It is a proton donor. A weak acid dissociates partially into its ions. It is also a proton donor. A Part 2. Carbonic acid forms a weak acidic solution in water. Write an equation to represent the change when carbonic acid is dissolved in water. We can write one of two equations. We can write carbonic acid plus water produces the hydronium ion and the hydrogen carbonate ion. Or you can write the equation without water and just ionize the carbonic acid into H plus and HCO3 minus. A Part 3. State two weak acids other than carbonic acid. We have ethanoic acid. We can use phosphoric acid or dihydrogen phosphate ion or ammonium ion or hydrogen sulfide. 2B Part 1. Define each of the following terms. pH. pH is a logarithmic measure of the H plus concentration in a solution, or pH is equal to minus log H plus ion concentration. pKa. pKa is a logarithmic measure of the acid dissociation constant Ka, or pKa is equal to minus log Ka. B Part 2. Calculate the pH of a 0.100 moles per dm cube aqueous solution of carbonic acid. The acid dissociation constant Ka of carbonic acid is equal to 4.5 times 10 to the minus 7 at the experimental temperature. So the first thing we're going to do is to write our equation of our carbonic acid dissociating. You can use the equation with water or the one without water. We're going to be using our ice table. So the initial concentration of the carbonic acid is 0.1. Initially, there is no reaction, so we produce no H plus ions or we produce no HCO3 minus ions. When the reaction starts, we're going to have a change of minus X for the carbonic acid. Because of the stoichiometric ratio being 1 to 1 to 1, whatever change you subtract on the reactant side, we're going to add it on the product side for each of the products. So we have for the change for carbonic acid minus X, the change for the proton will be plus X, and the change for the hydrogen carbonate ion will also be plus X. At equilibrium, we'll have now 0.1 minus X for the reactant, and for the products, we'll have X for H plus and X for HCO3 minus. It must be noted that because our initial concentration is large, it is 0.1, and the Ka constant is small, the change is negligible. So we're going to ignore the change so that we won't have two unknowns and we don't need to calculate this using the quadratic equation. So from that, we're going to write our Ka expression or our Ka equation, and Ka is equal to the proton H plus concentration times HCO3 minus concentration divided by the H2CO3 concentration. Now we must remember that H plus is equal to HCO3 minus concentration. And so in this case, we're going to have X times X, which is equal to X squared. So the Ka is now equal to X squared over the concentration of the carbonic acid, which is 0.1, equal the Ka value that was given in the question. We're going to make X the subject of the formula. So we say x squared equal 4.5 times 10 to the minus 7 times 0.1, which is equal to 4.5 times 10 to the minus 8. We're then going to find x by square rooting the value of 4.5 times 10 to the minus 8. So x is equal to 2.12 times 10 to the minus 4. This now gives us our H plus concentration. So the H plus concentration is equal to 2.12 times 10 to the minus 4 moles per dm cube. Once we have the H plus concentration, we can now find the pH using pH equal minus log H plus concentration. So pH equal minus log 2.12 times 10 to the minus 4, pH is equal to 3.67, which is approximately 4. B part 3. Determine the pKa of carbonic acid and compare its strength with an aqueous solution of hydrogen sulfide. The Ka of the hydrogen sulfide was given to be 8.9 times 10 to the minus 8. So what we're going to do is to find the pKa of the carbonic acid, find the pKa of hydrogen sulfide, and then compare them. So to find the pKa of carbonic acid, we're going to use pKa equal minus log Ka. Therefore, pKa is equal to minus log 4.5 times 10 to the minus 7, which is equal to 6.35. We are going to use the same equation to find the pKa of hydrogen sulfide, given the Ka of H2S to be 8.9 times 10 to the minus 8. So the pKa is equal to minus log 8.9 times 10 to the minus 8. pKa is equal to 7.10. Now note that the lower the pKa value, the more acidic the substance or the stronger of an acid the substance. So when we compare the pKa of carbonic acid to the pKa of hydrogen sulfide, we notice that the pKa of carbonic acid is lower than that of hydrogen sulfide. Therefore, carbonic acid is a stronger acid than hydrogen sulfide. B part 4. Sketch a labeled graph to show how the pH changes which occur during the titration of 25 cm³ of 0.1 mole per dm cube carbonic acid with 0.1 mole per dm cube of sodium hydroxide solution. The first thing you must realize is that carbonic acid is a weak acid, while sodium hydroxide is a strong base. We are measuring 25 cm³ of the carbonic acid using a pipette to be placed in a conical flask, and the sodium hydroxide will be placed in a burette. So we are adding volume of sodium hydroxide to the carbonic acid. Therefore, the pH must start low. So for a weak acid, it is going to be somewhere between 4 and 6. So the weak acid will start to increase in pH as you titrate the sodium hydroxide into the conical flask. You will then have a sharp rise when we reach the equivalence point, and then it plateaus when we have a higher concentration of OH minus ions than H plus ions. And so we have a rise in our pH curve. Part C. There are several buffers in the blood which have a pH of 7.35 to 7.45. C part 1. Define the term buffer solution. A buffer solution is a solution that resists changes in pH when small amounts of acid or alkali are added. C part 2. State the components of two buffer systems in the blood. Well, we have our phosphate ions, which is the weak acid and its conjugate base pair. So that's H2PO4 minus and HPO4 2 minus. So the one with the higher number of H plus ions is our acid, and the one with the lower number of H would be the conjugate base. Same thing for carbonic acid. We have a weak acid conjugate base pair. Or we could use our zwitter ions, which came from amino acid. So we have a weak acid and a conjugate base pair. C part 3. Explain using an equation how one of the buffer systems in C part 2 operates to maintain the pH of blood when acid is added. Now, because we're using this question to prepare for an exam, what I did was to look at if we add acid as well as if we added base, what would happen to the equation. So this, even though the question only requires the acid, in preparation for other exams, I included the base. So let's look at what happens when we add our acid H+ to our buffer system. Now, if you add H+ to the buffer system, what will counteract it is the conjugate base. So the H+ will be added to the base. Remember that the base is a proton acceptor. Now you'll form H2PO4-, which was already present in the buffer system, and this is how a constant pH was maintained. If you added OH- to the buffer system, then the acid would counteract the presence of OH-. And so the acid, being a proton donor, would give up a proton to the OH-, forming water. You also form the conjugate base that was already present, hence maintaining a constant pH. Or you could use the carbonic acid. If you added H+, then the base would counteract the H+ ion by accepting it, forming carbonic acid. If you added OH-, then the acid would counteract the presence of OH- ions, forming the conjugate base, which was already present, plus water. The water is neutral, so it does not affect the pH. You also form something that was already present, so the pH was not affected. Part D. Calcium hydroxide preparations are used in restorative dentistry as a therapeutic oral cavity liner. D. Part 1. Write the expression for the solubility product of calcium hydroxide. The first thing you must remember is that KSP deals with sparingly soluble compounds, which means that they are solids that dissolves ever so slightly. So our calcium hydroxide, being a sparingly soluble compound, is going to be in the solid state. It dissociates slightly to form calcium ions and hydroxide ions. D. Part 2. Calculate the solubility of calcium hydroxide in grams per dm cube. This is saying that they want the solubility in terms of mass concentration, not molar concentration. We're going to calculate the molar concentration first, however, and then convert it back to mass concentration. So the first thing we're going to do is to write our expression for KSP, or our equation for KSP. So KSP is equal to the concentration of the calcium ions times the concentration of the hydroxide ions squared. That is equal to the KSP value that was given in the question. Using our ICE table, we're going to calculate the concentration of our ions, which is our solubility. Solubility can be in mass concentration, grams per dm cube, or molar concentration, moles per dm cube. So bear in mind that solubility is dealing with the concentration of ions. From the ICE table, initially, we do not produce any moles or concentration of our ions. Our change are going to be plus x and plus 2x because our stoichiometric ratio is 1 to 2. Our equilibrium concentration, or moles at equilibrium, will be x for the calcium ions and 2x for the hydroxide ions. We're going to be looking now at plugging in our x values into the KSP equation. So where we have calcium ions, we place x, and where we have OH- ions, we place 2x. But remember that the hydroxide minus ions were squared. So we have KSP equal x times 2x squared. We're going to simplify this equation by saying x times 4x squared, which is now equal to 4x cubed. So our KSP is equal to 4x cubed. We can now find x. So x is equal to the cube root of the KSP value divided by 4, which is equal to the cube root of 5.5 times 10 to the minus 6 divided by 4. X is equal to the cube root of 1.38 times 10 to the minus 6, which works out to be 0.011 moles per dm cube. So our solubility is 0.011 moles per dm cube in terms of our molar concentration. But the question requires that we put our solubility in terms of mass concentration. We are then going to be using a simple equation. Mass concentration is equal to molar concentration times molar mass. So the mass conc is equal to 0.011 moles per dm cube times the molar mass of our calcium hydroxide. So it is 40 for calcium plus 16 for oxygen and 1 for hydrogen, but we must multiply that by 2 since in our compound we have 2 hydroxide ions. So once we calculate the molar mass, we can now work out the mass concentration. So 0.011 moles per dm cube times 74 grams per mole equals 0.81 grams per dm cube. This is our solubility in grams per dm cube. D part 3. Outline the experimental steps required to determine the solubility product of calcium hydroxide. So we're going to be looking at one of 2 ways. The first way is to find our OH minus ions using a pH meter. And we're going to use pH plus pOH equal 14 to find our pH of the OH minus concentration present in our calcium hydroxide. The next way is to carry out a titration using a standard solution of HCl. And then we're going to use that to calculate the OH minus concentration. And then we can use that now to calculate our solubility product. So let's go. 1. Add an excess amount of calcium hydroxide to a known volume of distilled water in a beaker. 2. Stir the mixture for a sufficient time to dissolve as much of the calcium hydroxide as possible to create a saturated solution. 3. Allow the undissolved excess solid to settle, then carefully filter the solution to get the saturated solution of calcium hydroxide. 4. Measure the pH of the saturated calcium hydroxide solution using a calibrated pH meter. 5. Repeat the pH measurement several times to get an average value for more accurate results. So the alternate method would be to perform a titration of the filtered saturated solution with a standard HCl solution to determine the concentration of OH minus ions using phenolphthalein indicator. We can then repeat the titration at least 3 times until the values are within plus or minus 0.10 cm cube for accuracy. This is the end of Module 2, 2019. Please remember to like, subscribe, and click the notification bell so that when new videos are uploaded, you will be notified. Thank you.